A particularly ironic statistic tells us that often drunk drivers suffer less serious injuries than sober drivers. This is because a drunk driver will stay relaxed on impact, whereas a sober driver will reflexively tense. By staying relaxed, the drunk driver unwittingly stays in contact with whatever surface they impact for longer, and reduces the collision force they experience. Airbags take advantage of this exact mechanism to keep drivers safer. This problem investigates momentum and impact time and their effects on collision force. For part A, picture a head-on collision between a car and a tree. We can calculate the force applied to the driver's head when it impacts the airbag with only a few given variables. First, a simple free body diagram can help us conceptualize this situation. At impact, a collision force F directly opposes the rightward momentum P. We can determine the momentum of the driver's head with the following equation, where momentum P is equal to the mass of the object m times its velocity v. Looking briefly at our problem statement, we have each variable needed to solve for momentum. Now that we have momentum, we can use this equation that relates the collision force F to the change in momentum delta P and the time in contact with the collision surface delta T. Next, we'll rewrite delta P and define it explicitly as final momentum minus initial momentum and substitute a few known variables. Recall that we were given the time the driver is in contact with the airbag in the problem statement. The final unknown variable can be found conceptually. Since impact with the immovable object will completely halt the driver's rightward momentum, we can call final momentum equal to 0. Now that we've calculated collision force, there's an important unit observation here. Kilogram meters per second squared can be written for clarity to the SI unit of force, the Newton. It is also important to note that our final answer is negative. This is simply because of the direction of the force applied. Since the force is being applied to the left, the sign is negative. If we were asked to calculate the magnitude of the force, this number would be positive. Continuing on, if we wanted to reduce the force on the driver by 20%, how long would the driver need to be in contact with the airbag? Let's start with our final answer for part A. 20% of our original force works out to about 153 newtons. Negative because, again, the force is applied to the left. Taking the difference, we can calculate the new force after being mitigated by 20%, F2. Now that we know how much collision force is being applied in this new situation, we can use this equation rearranged algebraically to solve for the contact time, delta t. Here we have our final answer, the time in seconds required to reduce the impact force by 20%. The benefit here is hard to overstate. In a potentially fatal crash, even small changes to airbag systems can really make a difference.